Hello guys, what's up? In today's video we are going to go through the pyCycle example, the Turbojet example of pyCycle, which is already on GitHub and is one of the few resources that we can use to get familiar with pyCycle and to learn it. So for the first example, we are going to start with a simple Turbojet, and I'm going to show you how to get this code. I'm going on GitHub. I'm going to search pyCycle. Oh, sorry. Let's search for it. GitHub.com. Let's go to pyCycle. Okay, now into the OpenMDAO pyCycle. Okay, we are going to have pyCycle here. And here it is, the code. Okay, and if you want to install it, you just have to pip install O and pyCycle all in your command window. You can also use your package manager in your IDE. I use PyCharm, and if I go just pyCycle, we are going to note install O and pyCycle. Okay, open source library for modeling of turbine based propulsion and power generation systems. Okay, so you can also click on install in here as well. So, and then you're going to need OpenMDAO as well, obviously, which you can just do the same thing. OpenMDAO in your package manager. You see I have it installed already. Or in your command window, you're going to write pip install OpenMDAO all, and it's going to install it. Okay, so we need OpenMDAO and pyCycle. Now, how to get this code? I'm going to go on GitHub and I'm going to search for it. I get to this page, OpenMDAO pyCycle. As you can see, OpenMDAO/pyCycle from GitHub. And then you see this page here. Now, into the examples of cycle examples, when you click on that, we are going to have some helpful examples, like with simple turbojet, with propulsor, simple turbojet that we are going to use, high bypass turbofan, mixed flow turbofan, and some other codes. Okay, now in the simple turbojet code, we are going to have this code. You can download it and put it in your virtual environment, which is the same thing that I have done, and you get this code. Okay, now if we click on the run and see what happens, we are going to have this code run. Okay, now when you run the code, we're going to see results like this. Now, this sort of result, this framework of results that is shown here is very similar to that of NPS's results, and we're going to have the attributions of our design point first, and then we're going to have our flow stations, and then the compressor, burner, turbine, nozzle properties, shaft properties, and then we're going to have our off design points. Okay, the results of the off design points are going to be shown here with the same sequence. Flow stations at first, and the compressor, burner, turbine, nozzle, shaft, and then the other point of other off design point, which is here Mach 2 and altitude 5,000 feet. Okay, so what the code will be like. Let's go through the code from the very first. Now, at first we have the import of the libraries, the OpenMDAO. This is the OpenMDAO.api as OM, the pyCycle as pyc, and it's going to write the code in the object-oriented structure. We're going to have our Turbojet class, which is using the pyCycle's cycle class, and it's going to inherit that, and then it's going to use that, but assign each values and attributions to it. Okay, so in the first part, as you can see in here, there's the use tabular equals true. Now, in the beginning of the code, we are going to have the ambient properties calculations. We're going to set that up. Now, pyCycle uses the CEA's ambient properties calculation as well as the tabular. Right now, it has these two methods. If you put use tabular true, you can use the tabular data, which is going to use some pre-calculated data. Whereas when you put the code to run on CEA method, thermal method equals CEA, it's going to use the NASA's JANF species data and calculate the fuel and air properties. Now, in both cases, as far as I know, it's going to use the Jet A fuel as standard fuel. And it's going to have the JP7 fuel as well. These two types of fuel are available to select in pyCycle. Now, by putting that into false, we're obviously going to use the CEA, and the results are going to be not much of a difference, just minor changes. But for most cases, they are similar to one another. Okay. Oh, I'm sorry. True. Now, inside a setup method of the class of the Turbojet, it's going to set up the code, set up the system, set up the components of the engine and the ambience properties calculation method. Okay, so now the design is going to be called as this way and like this design. Okay, now we are going to add the elements from now on. Self.add subsystem uses the OpenMDAO's add subsystem standard way to add the components for the engine. Now it's going to choose its name as FC for flight condition. As you can see, it is already using the pyCycle's predefined classes. pyCycle's flight conditions is going to be imported, added into a subsystem, and named as FC. And then the pyCycle inlets, it's going to assign its name as inlet. And the compressors, which is going to use the pyCycle's generic map data and extrapolation set to true for off-design calculations, if you had any, and then promoting the inputs. And this nmech is the rotational speed of the shaft, which contains the compressor and turbine. And then it's going to have burner, pyCycle's combustor class. And it's going to use the fuel type, which is already set to Jet A in here. And in here, it says that it is FAR, but as much as I know, it's literally the same as the Jet A here. And then the turbine, it's going to assign its name as turbine, and it's going to use its generic map data. And if you go to these source codes, you're going to see the data of the maps. Okay, and then Nozzle, which its type is going to be CV, which I think is the convergent, divergent variant of the nozzles. You can also set, I think, CD. You can go through the source codes, and then in here, as you can see, the nozzle type is set to CV, and the last coefficient is set to CFG. Now, if I go through the codes, the nozzle source code, we're going to see that the nozzle types are CD, CV, or CD, CV. Okay, and then as you can see, if set to CFG, the last coefficient, then gross thrust coefficient is an input. Okay, so we're not going through that, but by changing the nozzle type, you're going to find out the differences in the speed output calculation for the nozzle. Now after that, we're going to have the shaft, which is going to have 2 ports. Okay, and then its rotational speed is promoted as an input, because later on we're going to see that it's going to take the mechanical speed, the rotational speed of the shaft, as input. Okay, so why does it have 2 ports? Notice this is a single spool engine here we're using to model, and the number of ports equals to 2 is going to tell us that 1 port is going to be probably the turbine, and the other one will be the compressor. Okay, as you can see, we don't have any fan components here, like the turbo fan. We just have the compressor and the turbine. So it's going to have 2 ports for a single spool turbojet. And then there's a generic performance subsystem, performance, that it's not an actual component, but it's going to take the data and calculate the performance metrics of the engine. Okay, the number of nozzles is 1. Notice this is a single spool. It does not have any bypass nozzles, just the core nozzle. And the number of burners equals to 1. So now, by the time we reach here, the engine elements are defined in generic forms, and it's going to go connect the flow stations. Now in here, it uses the pyCycle's connect flow, and it's going to connect the output flow conditions of one component to another's input, and so forth. So it's going to have the flight conditions output flow connected to a target, which is the inlet's input flow. Notice this is flow out and this flow in. Connect W equals false here, in the case that I suppose the mass flow is not connected here. Only the flow properties like pressure, temperature, maybe speed, and so on. Okay, so, and then it's going to use the inlet's output flow connected to the compressor's inlet. Now, if you guys are familiar with turbojet engines, generic form of components sitting next to each other, you're going to find these connections very obvious. So there's the compressor's output flow connected to the burner's inlet, and the burner's outlet to the turbine inlet, turbine's outlet to the nozzle inlet, and so on. Okay, and then it's going to use the self.connect method to connect the compressor's torque to shaft torque. Okay, and the turbine's torque to shaft torque 1. Okay, torque 0 and torque 1. So it's going to have 2 types of torques for the shaft, which is connected to compressor and turbine respectively. And then it's going to use the connect method to connect a source, which is the flight conditions output static pressure, to nozzle's exhaust static pressure. Okay, note that in the engine, the output of the nozzle is almost 100% the ambient. So these are connected here, and it's going to connect the outputs to performance elements, which is going to use them to calculate performance metrics of the engine. So performance subsystem here needs some data from the station calculations. The inlet's output flow for the total pressure. Notice how you're going to define these in the standard ways pyCycle does. Okay, it's going to use the output flow to the inlet. Now, which parameter, the total pressure, is going to be connected to performance PT2. PT2 is the total pressure at point 2 of the engine. Point 2 is going to be the point where has the lowest pressure, okay? And then compressor's output total pressure is going to be performances total pressure 0.3, which dividing these together will give us the OPR of the engine. So it's going to need these two, the lowest pressure and the highest pressure of the engine, to calculate the OPR, right? And then the burner's fuel mass flow is going to be connected to performance designated mass flow for the fuel. And then the inlet FRAM, which the inlet component automatically calculates, is going to be connected to the performance ram drag variable. And Nozzle's FG, gross thrust, is going to be connected to that of the performances. Now, and then there's the tricky important part, the add balance for design and off design. You're not gonna have an engine just connected some sort of components and then you're gonna go with it. You're gonna need some conservations of mass, energy, momentum to be satisfied at the engine's cycle level calculations. Okay, so it's gonna use the a balance component. Now, what does this balance component do? Is that it is almost in a linear solver that's going to iterate over a parameter and then satisfy a set of objectives equals objectives like the thrust, which we are going to specifically set to a number, is going to be fixed, and then it's going to iterate the engine's total mass flow right here. So it's going to use self-add subsystem. It's going to name it balance. OpenMDAO's balance component here is used. And all of these are assigned inside of this balance variable. Okay? Now it's going to say if design. This means if you are calculating the engine at design point, so it's going to have a true value somewhere, which later on is going to be set to true or false, I think. This is generic form. It's going to use the balance component dot add balance. It's going to use a W with the units of pound mass per second with the equation units of pounds of force, which has the right hand side of the equation set to a target Fn. Okay, so this is the thrust of the engine, thrust requirements, the net thrust of the engine. And then the balance components, W, which is defined here, is going to use the inlet components, inlet flow, inflow, static, mass flow. Okay, and then the performances net thrust is going to be used from the balance left hand side W. Okay, now what this thing does, let me show you the article. In this article, which is an open source article from the MDPIs, from the developers of pyCycle, Eric Hendricks and Justin Gray, pyCycle, a tool for efficient optimization of gas turbine engine cycles. I really recommend reading this article. In this article, in the part where it goes through the balance components, is going to give you the equations that are needed to be satisfied at the engine level. Okay, this is it. As you can see, the residual should equal 0, such that the calculated net thrust of the engine is going to be equaled, okay, negated by the net target thrust of the engine that is specified by the user is going to be satisfied. Okay, the residuals of this equation should be 0. This means that this is going to set the Fnet calculated thrust of the engine set to the value that the user specifies. So how's that going to do that? It's going to iterate over a value, which is most importantly for this equation, the mass flow, in order to satisfy this equation and give you the thrust that you require, that you need. And then T4. T4 is the TIT, turbine's inlet temperature. The temperature for the outlet of burner or the input of the turbine. Okay, which in your case is going to change and iterate over the F, the fuel to air ratio, or the sort of equivalent to fuel's mass flow, in order to satisfy this equation and give you a design which satisfies your TIT requirements. Okay. Now these are handled inside the code using balance components. Okay. Now, in the balance component, you just gotta know these things in general, and then you start using them on your own. Now, the first, we are just trying to understand the code. We're not going to go way deep inside the code. So it's going to iterate over W, the engine's inlet static mass flow, overall mass flow, the air mass flow that is coming into the engine, in order to satisfy the Fn target that we have specified. And then it's going to do the same with the FAR, which is the fuel to air ratio, in order to satisfy a specified T4 target. Now the equation units is set here. This is just a default value in order to iterate. Don't you worry about these. And the same thing happens here for the shaft power calculations. It's going to iterate over the turbine's pressure ratio in order to satisfy the horsepower of the engine, of the shaft, in a way that the net power of the shaft is going to be 0. This means that the input torque that is provided to the shaft by the turbine is going to equal to the amount of the torque that is given to the compressor by the same shaft. So the amount of these is going to be set to equal to one another, but when added together, one of them is going to be minus, one of them is going to be negative, the other one positive. So the net is going to be 0. And it's going to iterate over the turbine's pressure ratio in order to satisfy this equation. And the same happens for the off design, but with slightly different parameters, like the rotational speed of the shaft, in order to have its own sort of objective to be equal. Now, going to the next part of the code, we have a solver set for the whole cycle of Turbojet Engine, which is the Newton solver in this case. And it's going to use a nonlinear solver to be Newton solver. OpenMDAO is already coming with Newton solver and a set of other nonlinear solvers which are going to help you with the calculations. In previous videos, we have shown a couple of these and worked with with 2 equations, nonlinear ones, and we iterated over a parameter to satisfy the equation using the OpenMDAO's nonlinear solver, which you can have it in here somewhere. And in here, it's using the same thing. It's just going to use the Newton's nonlinear solver in order to satisfy the calculations of the cycle level of the whole engine. Now, in here, it's just using some options for the Newton solver, like the tolerances, like relative tolerance, absolute tolerance, and the print level of the Newton solver's results and maximum iterations and solve subsystems equal true, which is going to use this option to calculate the inside of the components. So it's going to solve them as well. And then some options, which I'm not going to go through them. And then it is using a linear solver as well. And it's going to assign the OpenMDAO's direct solver for handling the linear calculations. And just a generic code here, super setup, to set up the whole setup class of the Turbojet of the Turbojet engine. And if you notice, by the time we get here, to the end of the Turbojet class, we have defined the generic form of our engine, its components, its nonlinear equations, but we haven't added any sort of variables to it, any values to it. So we're gonna do that later, and it's just gonna have the viewer function here defined in order to give us the results. I'm not gonna go through that for now. We're just gonna leave it here. Only in these parts, it's just gonna give us the headers of our results, the flow station names, the using the pyCycle's print flow station method, and then it's going to do the same thing with the pyCycle's print compressor, and then each component is going to have its own results shown and printed as well. Okay, turbine name, and using the design.turb dot the parameter, and then using the print turbine to give us the results. Okay, doing the same thing for the nozzle and the shaft. And then this map plots, I don't know why it doesn't work on my PyCharm's local run, but when I used to run this code on a notebook, let's say Google Colab notebook, this line of code gives you the compressor map and the turbine map of the engine. And then this is the important part, one of the most important parts. The class of, I think this is multi-point Turbojet, is going to use the pyCycle's pyCycle class, and it's going to add the actual point to the class that we defined our generic engine. Now that generic engine class that we defined earlier had already missed the design point, and the values for the components that it needs to calculate. Now, in this part of the code, we are trying to assign the values and the points to our engine. It's going to use the set input defaults for the design point that is used using pyCycle's addPoint method or function. And now, this is generic form of adding values, working with values and variables in pyCycle and OpenMDAO. Now it's going to use the design.nmech, the rotational speed of the shaft, for design point equals to the value of 8070 RPMs. The units, you can specify them or not. If you don't, it's going to use the default, and you just get assigned the default values. Now when you use these, if later on you're trying to optimize your engine, if you provide an external value to these numbers, it's going to take that. But if you don't provide the code with any values, it's going to use the input defaults. Now, this is the Mach number of the inlet component, set to 0.6, compressor's Mach number, burner Mach number, and turbine Mach number. And these Mach numbers, as far as I know, is the Mach number associated with the output of the engine. Output of the engine component specifically, like the turbine's outlet, burner's outlet, compressor's outlet flow Mach number, okay? And then we have the burner's dpqp. Now this is added to the engine as a pyCycle add parameter. pyCycle adds cycle parameter. This means that you can comment this and it's going to be fine. No burner dpqp is going to be considered for your engine. As long as you have it, you've added it, it's going to automatically consider this. Now, what is this parameter? This is the burner's total pressure loss with respect to its incoming total pressure. So this is exactly the pressure difference in total, let's say PT3 input pressure to the burner All these are total parameters. Input pressure minus outlet pressure of the burner divided by the input pressure of the burner. Now this is set to 0.03, which can be converted to the gas turb's efficiency for the burner. This means that almost the efficiency of the burner, which you cannot add it to the pyCycle, but in the gas turb, it's going to be equals to 97%, 0.97. Don't get me wrong, I hope what I said would be true. I've done it myself before, and I think it is the same. 1 minus this value gives you the efficiency for the burner that gas turb requires. Okay. Now, Nozzle CFG is a specific kind of nozzle loss coefficient. CFG, or the CV of the nozzle, is a loss coefficient. You're going to add its value here. We're going to talk about these later on individually in different videos. And then it's just going to define the off-design conditions that you require to run. Now, it's going to take the off-design points equals to, these are just the names of the off-design. Off-design point 0, off-design point 1. And the Mach numbers, respectively for each one, is almost 0 and 0.2. And then the altitudes are 0 and 5,000 feet. And then the thrust that is going to be required in these specific conditions is going to be 11,000 pounds of force and 8,000 pounds of force. And note, this comes from an experience that I had earlier with pyCycle, that if you want to set the Mach number to 0, it's better you don't set it to just equals 0. This is going to get you errors. Just put some tiny little number close to 0. Okay, so if you wanted to specify Mach number 0, specify like this, not the absolute 0, where it is used here for the altitude. Okay, that's it. And then it's going to use the off-design points conditions also added here, which is going to take these values and assign them to the off-design variables that needs values. So it's just going to using these parameters, these lines of code in a loop, to take these values and assign them to the respective variables in the off-design points, and the respective off-design points. And then it's going to use a generic form of pyCycle's design off-design connections. This is going to connect the necessary connections that are needed between the design and off-design calculations of the engine. Okay, and as you can see, one of them is here connected. It's just going to use default connections, and one of them is provided here. You can provide your own design off-design connections. Nozzles through the static areas connected to the balance components right-hand side of the W parameter. And then another super setup for this class, MP Turbojet. And this if dunder name dunder equal main is just going to ensure that if we ran this code directly, these lines of code are going to be ran. And then if you are using this whole code and import it into another OpenMDAO's generic framework and problem structure, you need to assign these values in that framework. But if you are running the code here right now in the pyCycle, you have other framework setups to go through and do. One of them is, in any OpenMDAO code, you're going to need your problem structure set up and defined. So we are going to have a problem which contains our whole OpenMDAO and pyCycle framework and calculations, which has its own subsystems. So we're just going to have our problem, and inside our problem, we're going to have a model. And that model is going to be the multi-point turbojet class that we define here that has the turbojet's generic class that we defined inside itself. So when you're going to use, whenever you needed to import your engine model, you're going to use this class. This class includes your turbojet's generic code with its components and balance components and the names and etc. and the values here. And this is going to be your model inside your problem, OpenMDAO problem. And then you're going to set up your problem, and then you're going to set the values that are necessary for the calculations. These are the performance metrics and important parameters that you need to provide to the code. The design's flight condition, altitude is going to be 0. And the flight conditions Mach number is going to be 0. This represents, I suppose, the sort of SLS condition, static sea level condition, or in some cases the takeoff condition. In the takeoff condition, we almost assume that the speed of the aircraft is 0. The speed of the airflow coming to the engine is almost 0. We're just going to assume. So its Mach number is going to be close to 0. And then the altitude is obviously assumed to be 0. So this is the SLS condition. And then we are going to have our engine to have this value of thrust. Notice we have defined balance component to converge the thrust to this value, 12,350 3-pounds of force. And then we're going to have the T4 target, the TIT of our engine, turbine inlet temperature, 2003.67 degrees of Rankine. You can obviously set other units, like I think Kelvin. Your compressor pressure ratio is going to be defined like this. Design points compressor pressure ratio is going to be 25. Compressor's isentropic efficiency, I think this is isentropic efficiency, 0.83. And it's going to use these values to calculate the compressor's polytropic efficiency inside the generic compressor components and method of pyCycle. And your turbine's efficiency, notice the turbine's pressure ratio is not going to be provided. It's going to be calculated using the balance component, which takes the turbine's pressure ratio as input, as a variable, iterates over it to satisfy the torque requirements for the shaft. And then the initial guesses, the initial values. Now, I think these guys have used different sorts of setting the values, like prop.setval that we have seen earlier in OpenMDAO's videos. In the OpenMDAO, you're going to use prop.setval, okay? And then you can also use the prop in your variable equals to the value 1 to assign. Now, these are the components that are used. So now, these are the values that are used as initial guesses for balance components. So these values that you are providing to the code are going to be the guess, good guesses. And it's going to be used to iterate in order to find these values. So these are not the exact values. They might change in calculations. And then some other values for the initial guess in the off design point. And then this time. This is only used, import time, to just track the time that is passed for your model. This is not so much important. You can just delete these lines. And the solver print here just specifies the level of details that is provided to you by the solver print results. Okay, and this prop.run model in the OpenMDAO just runs the whole model and is going to give you the results if you have called the results to be shown. Okay, and then in here is just going to use the design points viewer function, which is provided the prop, that is OpenMDAO's problem-specific framework, and then the points, which is design, and call the viewer function here to give us the results, and the map plots to give us the maps of the components, which I don't know why when I run it locally it does not give me the maps. Okay, now let's run the code and see the results again. I just ran the code and I'm going to see the results here, and this is it. It has paused 2 and 0.7 seconds because I had already ran the code, and this is going to run easier this time. Now in here it's going to give us the results of the design points, the max 0, the altitude 0, and the engine's calculated mass flow. Let's see if the value was different. The mass flow provided was 168, as you can see, but the calculation converged to another value because the thrust needs to be converged to the value that we have specified here. Okay, and this is your gross thrust, this is your net thrust, this is the ram drag, which obviously equals 0 when you have the Mach number 0. The OPR is 25, and the TSFC is calculated to be 0.64 pounds of force over hour times pounds of mass. Pounds of mass over hour times pounds of force. And then the flow stations are here, flight conditions, outflow, output of the flight condition component is going to have the following: total pressure, total temperature, total enthalpy, the entropy, I suppose, the static pressure, the mass flow, Mach number, velocity, pounds, feet per second, and the area that is calculated, and then the inlet's outflow. But by the time here, it equals the ambient pressure. Okay, so the inlet does not have any pressure losses considered. The total temperature, 518.67 rankings. Okay, let's see the value if we had provided. Yeah, 6.6. This was the initial guess, but the calculated value is found to be this. And then we're going to have the results, the compressors, corrected mass flow pressure ratio, adiabatic eta efficiency, the polytropic efficiency, the corrected speed, the power, the R line of the compressor map, and then so on. Surge margin and other parameters. And then the burner is going to have a dpq that we have specified, its output temperature, the fuel mass flow, and then the FAR, fuel to air ratio. So some of these results are the inputs that you have provided, like dpqp, and this one, which is your TIT, the T4 target, which you had set to be this value, to 2003.67. But some of them are actually calculated. So not all of these are outputs. Most of them are. And then the turbine properties, just like the compressor properties, nozzle properties. As you can see, your CV is NA, not applicable, and your CFG is considered to the value that you have provided. The throat, the Mach number for the throat area, Mach number of the throat, the output of the nozzles, Mach number, the speed, and then the gross thrust. And as you can see here in the shaft, the mechanical speed, the rotational speed, 8,070 RPMs, and the input torque to the shaft, which is almost equal to the input. Okay, output torque, input torque, and then the output power to the input power, and these are almost equal because it might use some of the power for other uses. We didn't see that here, but in a turbofan engine it has. Maybe it's that parameter, I'm not sure. But these are almost equal to one another. And then the results for the off design points are provided here. Now this is the code for the Turbojet Engine model, performance model by the pyCycle. And then if you find this video to be helpful, we're going to go through the turbofan engine's code and then see much more details like bypass ratio, bypass nozzle, maybe the mixed flow turbofan. These are different types of examples of the pyCycle that needs to be elaborated more. I hope you guys find this videos useful, so please don't forget to share, like, subscribe, and leave any comments, any questions that you had, and I will try to address them as soon as possible, as much as I can, and as much as I know. Thank you guys.